So, picking up where we left off, this is Monday, this is October 28th. This is sort of part 2 of the optimization notes. And it uses stuff that we already know, we're just putting it on word problems. The idea is maximums and minimums occur where there is a critical point. So we take a derivative, we set it equal to 0, and then we do something to test to see to make sure it's a max or a min. Right? You wouldn't want your boss to tell you to maximize profit, and then you give him the answer that actually minimizes profit. That would be bad. You want to make sure that the answer you're giving is a max rather than a min, or a min rather than a max. Whatever it asks for, we've got to make sure we're giving the right thing. Now, the ones from Friday, they were almost all parabolas. In fact, the examples were all parabolas. So if you knew which way the parabola was facing, then you would know that your critical point was a max, or a min if it was the other way. So those weren't too bad in terms of knowing if your critical point was a max or a min. Today we may have to be a little more careful. All right, so number 4. A manufacturer wants to design an open box having a square base and a surface area of 156 square centimeters. What dimensions will produce a box with maximum volume? Okay, goodness. So we got an open box with a square base. So I'm going to draw my square base to start with. So those dimensions will be x and x because it's a square. And then we've got to figure out how tall the box is. This is art class today. You can draw a 3D box. What dimension do you want to use for the height? Doesn't matter. Just what letter do you want to use? H it is. Okay, so there's the picture of what's going on. It's an open box, so that won't matter for volume, but it will matter for surface area. So we need to be careful about that. Surface area of 156. So something equals 156. Surface area, that's adding up all the areas. So we've got our base area. That would be x squared. And then what's the area of each side? Of this side? That's not x squared. That's xh. And how many of them are there? How many xh's? 4 of those. So x squared plus 4xh equals 156. Okay, but that's, would you say that's our secondary equation, or is that our primary equation? Do you remember what those words mean? Primary is the one that we're going to maximize, the one that we'll take a derivative of. Secondary is like the helper that will help us get an answer. So are we going to take a derivative of that one? Is that what we want to maximize? Or is that just going to be our helper equation? Let's see, what else do we know here? What dimensions will produce a box with maximum volume? So what's the volume of that box in terms of my variables? X squared h. All right, let me ask it again. Which of those equations do we want to maximize? The first one or the second one? Oops. I heard both answers there. Maximum volume. So I want to maximize this one, the second one. That makes it my primary equation. That's the one that I'll take a derivative of. Except that I don't want to take a derivative right now. Why don't I want to take a derivative right now? Because there's an h. That's one way to say it. But it's not just that there's an h. Like if it was all h's, it would be fine. There's two variables. There's an x and an h, which means I could take a derivative, but it would require the product rule, and I'd have a dx and a dh. Ooh. So I want to use this helper equation to get my primary equation into having only one variable. So would you like to solve for h or for x in this first equation? I think that's an obvious answer. Do you want to solve that for h or for x? Definitely h, right? To solve for x, you'd have to use the quadratic formula and have h's and ew. Let's solve that for h. So 4xh equals 156 minus x squared, which means we can divide by 4x. H equals 156 minus x squared over 4x. And I could split that up. I don't think I want to split it up yet. Let's now plug all of that in for h. So volume is x squared times 156 minus x squared over 4x. Okay, right now I could take a derivative of that, but that would be product rule and quotient rule. Like, let's distribute the x squared. Well, there's a lot going on here. Just don't want to mess up the algebra. So I'll show the steps. 156 x squared over 4x. Thank you. Minus x to the fourth over 4x. So 156 over 4. Be nice if that divided, and I think it does. 40 times 4 would be 160, so 39x minus x cubed over 4. Okay, that was a lot of work for that. Let's see. I'll need to take a derivative, set the derivative equal to 0, find the zeros. I need to be careful though. This is an x cubed. In fact, it's a negative x cubed. So it looks something like that if I graphed it. That means I should find two critical points, and one will be a max and one will be a min. So I'll need to be careful about, once I get my critical points, I'll need to be super careful about which one's the max. Alright, dv dx equals 39 minus 3/4 x squared. Set that equal to 0. So I'm going to move the 3/4 x squared over. And then multiply by 4/3. So x squared equals, let's see, 39 over 3 is 13. Times 4 is 52. So what does, so x equals square root both sides. Don't forget the plus or minus. Plus or minus the square root of 52 for my two critical points. This works out well because I know which one to use and which one to throw away. Because look at my picture. Which one of those answers is legit? The positive one, because I can't have a negative side length. So we're only going to use the positive one, because that's the only one that makes sense. We can also sort of reason through that the negative one is right there. The positive ones are right here. So I know that that's a maximum. Or that makes a maximum. Okay, I've done all the hard work. Have I answered the question? Yeah, not quite. What dimensions will produce a box with maximum volume? What dimensions? So I've got my x dimension. My h dimension is right there. I think I have a safe stop in my near future here. 156 minus, well, I can square the square root of 52 easy enough. Over 4 square root of 52. And what the heck, let's stop there. There's more we could do, but why bother? Leave it alone. Safe stop that. Number 5. A cylindrical metal container, open at the top. More pictures, artwork. Cylindrical metal container, open at the top, is to have a capacity. Capacity? What's that a fancy word for? Doesn't mean maximum. It means volume. That's how much it can hold. So as to have a volume. Units could help with that too. Inches cubed would be volume. Capacity of 54 pi inches cubed. The cost of material used for the bottom is 50 cents per square inch. So for the bottom, let's see if I can try to. It's 50 cents per square inch. And for the curved side, so this stuff is 25 cents per square inch. So maybe the bottom's made out of something different. Maybe the bottom is like thicker. Who knows? Find the dimensions that will minimize the cost of the material. Okay, so it's got a set volume, meaning we could make it like super tall and skinny, but it would have to be really tall, so that would cost a lot to get the sides would cost a lot. Like the bottom wouldn't cost very much. I guess the other extreme would be you could make it like super, like this. But that would mean the bottom costs a lot. And so somewhere in the middle, we got to figure out what's the cheapest way to make a can that holds 54 pi inches cubed. So you could see where this is like a real world problem. If you're wanting to sell, I don't know, you wouldn't put it in this term. This is just going to make the math easier. But if you want to sell a certain amount of liquid, and you want to make your packaging cost as small as possible, well, then you got to figure out, well, what size cylinder do I need? And that's the question. Like, what dimensions will be the cheapest for this cylinder? So I'm trying to minimize the cost, so I need an equation for cost. And then we'll take that derivative, set it equal to 0, check to make sure we've got a minimum rather than a maximum. Okay, so we don't have, we're going to have to come up with this formula on our own, right? Like, they don't give us a formula for the cost of a cylinder. But I think it's going to be try to do it in words first, the cost of the base plus the cost of the curved side. Cost of the base, cost of the curved side. Okay, well, the base is 50 cents per square inch. The units are a help here. 50 cents per square inch. So if I want cost, I need to be multiplying by square inches. I need to be multiplying by the area of the base. Well, that one's easy. That's just pi r squared. So the cost of the base would be the area of the base times the per area cost of the base. So 50 cents times pi r squared. The cost of the curved side, it's only 25 cents per square inch. What's the area of the curved side going to be? Thinking about like unfurling it here. We need a height. And we have a radius. So if I think about the label on a soup can, a label on a soup can looks like that. There's my soup can label. If I unfurl it, it makes a rectangle. Length times width for a rectangle. So the height of the rectangle is the height of the soup can, no big deal. But what about this length of the rectangle? Circumference. So what is the... I don't want to just do circumference times height. I have a formula for circumference. What's the circumference of a circle? Did I hear a 2 on that? 2 pi r. So the area of the soup can label would be 2 pi r h. 2 pi r h. Okay, so let's clean this up a little bit. So cost would be 0.5 pi r squared plus 0.25. You know what? Let's do 2 times 0.25 plus 0.5 pi r h. Combining the 2 and the 0.25. Alright, that's what I want to minimize. Why don't I like that as an equation to minimize? 2 variables, right? I'd be doing product rule over here, and I don't want to do that. So I need an equation that ties together r and h. Well, they told me that the volume was 54 pi. How about the volume of my can? The volume of a cylinder? Let's see, area of the base times the height. So pi r squared times h. So that'll be my secondary equation, my helper equation. I'm going to get rid of the pi right now, divide both sides by pi. And you tell me, would you like to solve for h or for r? Do you want to solve for r? I would, if you solve for r, you're going to have to do a square root. So I think I would solve for h. So h is 54 over r squared. So my expression for h can go in over here. So c equals 0.5 pi r squared plus 0.5 pi r 54 over r squared. Okay, so now I have an expression for the cost only in terms of r. So let's clean up the algebra and then we'll take a derivative. Well, actually, let's clean up the algebra first and then we'll see if we can learn anything. Half of 54 is 27. And we end up with an r in the bottom. Okay, so unlike the previous problems where I could like do a little sketch and know like how many maxes and mins I'd have, I have no idea what this looks like, right? This is a parabola and then like a reciprocal, so like I don't know ahead of time what this graph looks like, so I don't know what to think in terms of like how many maxes and mins and where they are. I'm going to have to do something to figure this out. Okay, so C prime. Or I guess if we really wanted to be fancy about it, it's dC dr, the derivative of C with respect to R. So pi r, that's the first one. That's an easy one. Remember that 27 over r, or r in the bottom, is the same thing as r to the negative 1. I hope I'm not skipping too many steps. Minus 27 pi r to the negative 2. Okay with that? Do I need to show some steps in between there? The derivative of r to the negative 1 is negative r to the negative 2. So I get my negative sign, and my exponent goes down by 1. All right, set that equal to 0. Let's see. So I'll move the 27 pi over r squared over equals pi r. And a little bit of algebra in my head. They've done us some major favors here. Why do I say that? What can we do next? Algebra-wise, what can go away? Pi's will go away. And then if I multiply r squared to both sides, I get r cubed. And so r equals 3. The trick is, I have no idea if that's a positive or a negative. I mean, a min or a max. So it's a critical point, but I don't know if it's a critical point because it maximizes cost or a critical point because it minimizes cost, which is pretty important, right? Like, you don't want to give the boss the entirely wrong answer and cost the company money. So let's do a sign chart for, I guess, for C prime, to know if we're positive or negative here. Okay, so here's C prime. I was going to check 0, but that wouldn't work because that would mess that up. So I'm going to check 1 and 4. And again, I'm only looking for positives or negatives, so I don't really care about the pi's and the exact values here. So if I plug in 1, I get pi minus 27 pi over 1. And I don't have to be a computation expert here to realize that's negative. So my cost is decreasing there. If C prime is negative, then C is decreasing. If I plug in 4, I get 4 pi minus 27 pi over 16. And again, I don't know what 27 pi over 16 is, but 27 over 16 is less than 4, so this is positive. If C prime is positive, C is increasing, which means R equals 3 is a minimum. Okay, calculus is over. Now I got to figure out, to answer the question correctly here, find the dimensions that will minimize the cost. Okay, so I got R equals 3. Next I need H. 54 over 3 squared is 6. So a radius of 3, a height of 6 would minimize the cost. And then find the minimum cost. So I actually need to figure out what the cost would be. So that I need an equation with C in it somewhere. And I've got 5 different equations with C. They should all work. So I guess let's just pick the, I don't know. I could pick the one with H in it, or I could pick the one with only R's in it. It doesn't matter. 0.5 pi r squared plus 27 pi over r. Safe stop. 4.5 pi plus 9 pi. I should probably safe stop this before I mess something up. $13.5 is the cost. It's an expensive can. But that's the least expensive can that will hold 54 pi inches cubed, where the bottom costs 50 cents per inch squared and the around the side costs 25 cents per inch squared. That is a heck of a problem. Which means we'll do number 6. I don't think we'll have time to do number 6 right now. Let's turn to the homework and we'll do number 6 probably tomorrow. Reminder, Friday's assignment was 1 through 6, today's assignment 7 through 13. You got a Schoology quiz that's due Halloween night because it's super spooky and scary. Let's look at number 11. I think we can do a number 11 in 8 minutes. A book publisher designs the pages of a book. Oh, yeah. A book publisher designs the pages of a book to contain 24 square inches of print on each rectangular page. The margins on the sides and bottom of the page are 0.5 inch. The margin at the top of the page is 1 inch. Try to draw this sort of to scale here. So the top margin is 1 inch. The sides and bottom margins are 0.5 inch. And the inside area, like the print area, is 24. What should the dimensions of the pages be? So not of the print, but of the total page, so that the least amount of paper is used. Okay, so I want to minimize the area. I think I'm trying to figure out. I'm going to use X and Y, but do I want X to be the full width or the width of the print? And I don't guess it matters, except that it asks me for the dimensions of the page, so I may as well go ahead and set this up to make the dimensions of the page, the entire page, be the X and the Y. So it'll make this equation easy. I think I'm going to have one hard equation and one easy equation. The area of the page is XY, and that's what I want to minimize. Okay, but something equals 24. Like this inside area is 24. So what do I multiply to get 24? What's this width? It's X all the way across.
X minus 1.
X minus 1. Minus a half from one side, minus a half from the other side. So that's X minus 1. And what about the height of the printed part? Y minus 1.5. Yeah, because it's half inch on the bottom, but I have 1 inch on the top. Okay, so I want to minimize xy. That's the one I want to take a derivative of, but not yet because I've got x's and y's. So I need to solve this for x and y, or x or y. Neither one of those looks great. I guess let's solve for y. So I don't want to FOIL that thing out because that would make it worse of a mess. I'm going to just start picking off the layers. So I'll divide by x minus 1. And then add over the 1.5. So that's my expression for y. So all of that is going to go in for y. So x times 24 over x minus 1 plus 1.5. So 24x over x minus 1 plus 1.5x. What's it going to take? That's why I'm like pausing. I don't think I can do anything else. What's it going to take a derivative of this thing? Quotient rule. Okay, gf prime. So x minus 1 times 24 minus fg prime. Oh, that wasn't too bad. All over x minus 1 squared plus 1.5. This is going to be ugly. In fact, it's multiple choice, so I think my guess would be, you know what, forget that. Let's go look at our answer choices and see which one gives us the least amount of paper. Now, I have to be careful here. 6 times 4 is 24. But if that's the dimensions of the whole thing, that won't give me 24 inches of print on the inside. So that's not good. 8 times 3 is 24. Okay, that's fine, but that's the overall dimensions. That's not going to give me 24 inches of print. 9 times 4.5 or 5 times 7.5. I'm guessing both of those would give me 24 on the inside. This would give me 8 times 3 is 24 on the inside. 4 times 6 is 24 on the inside. So it's one of these two. I just need to know which one of those is a smaller number. Let's see. 9 times 4.5 would be 36 plus 4.5. 40.5. 7.5 times 5. That would be 37.5. So 37.5 is smaller, so it would be D. We cheated by using the answer choices. But it's not cheating, it's understanding what they give you and doing what you can with that. Okay, so try some more of those problems. Like, some are pretty easy, ones where they just give you an equation, like 1 through 6, and then they start to get kind of hard, like the ones we worked on today.